Alright, so in this video we're going to learn about a couple other characteristics of a parabola. And I know you're thinking, wait a minute, we already learned about an axis of symmetry, a vertex, x-intercepts, y-intercepts, increasing intervals, decreasing intervals, minimum heights, maximum heights, domains, ranges. How many more characteristics can there be? Yeah, I know. But I would point out that what we're talking about today gets us to one of the main applications of parabolas in the real world. And yes, they are incredibly applicable, actually. You have seen them and you use them every day, whether you're doing it intentionally or not. So, or you probably use them every day, or at least every week. Maybe not. Maybe you're off the grid. I don't know. Anyway, we're going to focus on the focus of a parabola. You see what I did there? Focus, focus. Yeah. So, what we're going to do here, we've got this image, right? That looks fun. We have these rays coming in to this, which is a parabola. So vertical rays enter a satellite dish. Hint, satellites are one of the applications of parabolas, whose cross-section is a parabola. When the ray hits the parabola, they reflect at the same angle at which they entered. Draw the reflected rays so that they intersect the y-axis. So keep in mind, this angle here is the same as this angle here. That's how the reflection works. So if I draw these reflected rays, this ray here, whoops, that's not what I want to do. Is going to be kind of like this. Now I know this is easier for me to do on a computer maybe than for you to do freehand, but this is what it's going to look like. So this right here, where again this angle should be very similar, should be exactly the same as this angle. Now I'm freehanding this, but they look pretty close. And then this one is going to go like that, where this angle here should be pretty close to this angle here, or technically it should be exactly the same. So those are the rays that we're talking about. Now, what do they all have in common? Well, they should all intersect at the same point. So that's what they have in common. And that point is on the y-axis. So the optimal location for the receiver of the satellite dish is at a point called the focus of the parabola. Determine the location of the focus, explain why this makes sense in this situation. So if I look at this picture here, the location of the focus looks like it's at 0, 1. Why does that make sense in this situation? Because that's where all of these rays reflect to. And so herein lies the application. All parabolas have what we call a focus. And one of the applications is satellite dishes. So when I say you use this every day, well, you may or may not have satellite TV at your home, but if you ever use GPS, that has a satellite dish. That uses satellites, right? Global positioning system. When you're using your phone, a lot of the cell towers use parabolic dishes to receive and send signals. So that's why I said you're most likely using this all the time. So what it does, or what the feature of a parabola is that we care about, is that any signal that comes into the parabola will reflect off of the parabola, and it will always go to that point. So when you see a satellite, if you have satellite TV at your house, or if you've just seen a picture of a satellite dish, that node thing that's in front of the dish, that is the receiver. That is always designed to be at the focus of that dish. so that every signal comes in, gets sent to that node, and then you can receive it. And that's why when you think about like satellite TV, right? You aim this little dish on your roof to hit a satellite that is really far away. And part of why that works is you don't have to be spot on. You just need the signal to be able to hit the dish at some angle, and then your TV will be able to receive it. That's math for you. Okay, similar sort of application, but in the opposite direction. So beams of light are coming from the bulb in a spotlight located at the focus of a parabola. When the beams hit the parabola, they reflect at the same angle at which they hit. Draw the reflected beams. What do they have in common? Would you consider this to be the optimal result? Okay, so now when I draw the reflected beams, what are they all going to do? They're all going to go straight out. So now we're sending a signal from the focus, and that signal in this case is light. But if the light hits the parabola, then it's going to bounce off at the same angle at which it hit, which is always going to be straight out from the parabola. So this is another application of the parabola shape, and that is for, think of like spotlights, flashlights, headlights, any sort of light that's in an encasing is usually parabolic, so that the light from the bulb shines in all directions, but anything that's not going in the direction you want will reflect off of the parabolic shape and shoot out in the direction that you want, so that all of the light is focused. Other examples of this is, think about like anytime you use the word focus, like cameras, things like that. Okay, so let's talk a little bit more about this and how this comes into play with parabolas. So previously we learned that the graph of a quadratic function is a parabola that opens up or down. A parabola can also be defined as a set of all points x and y in the plane that are equidistant from a fixed point called the focus and a fixed line called the directrix. So if we have to learn about the focus, we also have to learn about this line called the directrix. The focus is in the interior of the parabola and lies on the axis of symmetry. That is very important that we make sure we understand that. The focus is on the axis of symmetry. The vertex lies halfway between the focus and the directrix. Also crucially important, the directrix is perpendicular to the axis of symmetry. So here's the focus, here's the vertex, here's the directrix. The red line is the axis of symmetry. So the directrix and the axis of symmetry are perpendicular. And then, depending on if you've taken a geometry class or not, you recognize that this symbol right here and this symbol, that means that these two segments are congruent, or the same length. So this length here and this length here are always the same because the vertex is halfway between the focus and the directrix. How do we find this? We use this new letter, not new, but we haven't seen it yet, called P. However, we have a nice relationship between P and the A value that we are used to seeing. So P is the distance that we just talked about. That distance from the focus to the directrix is P. So if the vertex is at 0, 0, then the focus is at the point 0, P, and the directrix is at y equals negative P. So this is P, and this is P. And in terms of the A value that we're used to seeing, that's right here. So A is 1 over 4P. Okay, so if you're confused, let's do some examples and hopefully this will make a little more sense. So here I have a picture of a parabola where the focus is at 0, 2, and the directrix is at y equals negative 2. We want to write an equation of this parabola. So the first thing I'm going to do is I'm going to recognize that this is P, so P is 2. And so then I know if A equals 1 over 4P, then this is 1 over 4 times 2. So A is 1/8. And if the focus is at 0, 2, then I know my vertex is at 0, 0. because the x-coordinate of the focus has to also be at the same as the x-coordinate of the vertex, and the vertex lies halfway between the focus and the directrix, and since this is at 2 and this is at -2, 0 is halfway in between. So I know the equation of my parabola is y equals 1/8 x minus 0 squared plus 0. You don't have to write all of that. We could just say y equals 1/8, and I miswrote that, sorry, 1/8 x squared. And again, just if you're confused, I talked about it, but I didn't write it. My vertex here is 0, 0. There we go. Let's try another one. I want you to try this. Pause the video, write the equation, unpause when you are ready to check. Alright, so hopefully you got y equals -1/12 x squared. How do we come up with that if you're confused? Well, notice the focus is at 0, -3, so the focus is below the x-axis now, and the directrix is above because it's at y equals +3, so therefore my p-value is going to be negative, and specifically it's going to be -3 because I went down 3, here I went up 3. So a is 1/4 times -3, which is -1/12. That should be negative because the parabola opens down. My vertex is still at 0, 0, so it's y equals -1/12 x squared. Alright, so let's try an example where we're given the equation and we want to find the focus and the directrix and all of that fun stuff. So here, if I look at A, I know that, I meant this A, so I remember that A equals 1/4p in terms of the equation. In this case, A is 0.5. That's the same as 1/2 equals 1/4p. So I need to find p. So let's multiply both sides by 4p. And so when I do that, this goes away. 4 and 2 reduce, and I get 2p equals 1. So p equals 1/2. I want to point out it's a total coincidence that the p-value and the a value came out to be exactly the same here. We should understand that's a coincidence because we haven't seen that on the other problems yet. So p is 1/2 though. This is a positive a value, so that means that if the vertex is at 0, 0, that the focus, so the vertex is at 0, 0, so the focus has to be a distance of p above that. So the focus will be at 0, 1/2. The directrix will be a distance of p below that. And we know the axis of symmetry is the h-coordinate of the vertex. So that's x equals 0. Alright, I want you to try and do b. My hint is first let's just rearrange this and make it y equals -x squared. Okay, so now go ahead and pause the video, try and do b. Alright, so here I set -1 equal to 1/4p, and then I multiplied both sides by 4p, so I got -4p equals 1, p equals -1/4. My vertex is at 0, 0. So my focus then, since this was negative, had to be below, so it's going to be at 0, -1/4. The directrix is going to be then above at y equals 1/4, and my axis of symmetry is x equals 0. Okay, so the big thing we want to understand is the relationship between A and P, and that P is just the distance from the vertex to the focus and the distance from the vertex to the directrix. The directrix is perpendicular to the axis of symmetry. The focus is always inside the parabola. The directrix is always outside of the parabola.